is there any questions before I start the new lecture? Okay. So, if you remember, we were talking about RTL combinational components. Yeah, remember? We talked about decoder, we talked about multiplexer, but not finished it. Now, instead of continuing the lecture on combinational, I switched to sequential part, so you would have something to use in your projects, because most probably you need this design in your projects, and also be able to do the labs. So what we do now is going to memory elements. We call it memory elements. We talked about what is RTL. We talked about decoder and multiplexer, but didn't parity, comparator, and other. We will talk about it later. Now we are going to talk about combinational versus sequential circuit, and then we start with a latch, then go for another kind of latch, and then we go to flip-flop. Do flip-flop and introduce the flip-flop to you. So the first thing, I guess we have talked about this before, yeah? Am I right? I told you something about sequential versus combinational. So what would be the main difference between combinational and sequential? Could you tell them? Like and or and these things. So the output will be determined by what in combinational? The output is going to be determined by inputs. Is that right? So if you have an AND gate, you change one of the inputs from 1 to 0, for example, the output is changed accordingly. Yes? But in sequential, it's not only on inputs. What else? It has, yes? Time. What do you mean by time? What? No, not in that context. Yeah?
The inputs and the state of the system?
The state of the system. What do we mean by a state? Don't know.
What it is at that time?
But it is something. Yeah. Some kind of, yeah. So it has some kind of concept of memory. Because when we talk about memory, we think of something that stored something inside it. Yes? Memory is that. Storing something inside. For example, our memory, our brain, is storing so many things in it. We call it memory. So it is some kind of memory, and which we are going to talk about memory elements now. The state is the whole context of the current situation of the circuit, which has been generated, has been formed by the previous inputs during the time. So it is not something instantaneous. You can say, okay, I change the input to something, then I expect the output changes. No, it is not only dependent on the inputs. The output is dependent on the inputs and some kind of the status of the circuit now. So the circuit has something from previous times. So by time, if you said time, I thought maybe you are going to talk about this, not the delay. Yeah, the delay is always there. So whenever we have something, some circuit, there is the delay, but it's obvious. Yes?
So can we think of state as in like the whole culmination of every like action on circuit, and then memory is just one part of the circuit that keeps track of the different inputs?
We can say that, but it is just a definition that gives us an idea that a state is something there, but it doesn't give you what is a state. So what's it? It's a combination of everything there, which is there. We will see the examples today. So how could we have some states? So in a combinational logic circuit, whatever the function, the output would be a function of input. That's it. So if you change the input, the output might change or might not change. It's not always that. For example, in an OR gate, when we have 1, 0, then you change 0 to 1, it still remains 1. But the output is determined by the inputs only. So we can write W is a function of J. J is the input set. However, in a sequential circuit, you can see the idea gradually. There is something coming back from the outputs to the circuit, from the outputs. This is what we call a state. So the function of the circuit does not only depend on the inputs, but also depend on something else, which we call it a state. And where does a state come from? From the circuit, from itself. The combination of whatever here it is, it will form some kind of a state for us, and the state comes from there. Okay? Yes?
So is the state in the previous data then?
It depends on the previous data, not just the previous data. Maybe the previous data, the one before, they are just accumulating and making a state. It's not just one, for example, cycle before.
Like the continuous results?
Yes, yes. So it's always changing, and it's the result. Yeah. Okay. So this is the sequential circuit, and we can say that it is not dependent only on inputs. So W is not only determined by inputs, but it is dependent on the previous function of the circuit. So we had inputs coming, then changing, then changing, then changing. All of these inputs have some kind of effect in the output. So we can write the function as Ji. Ji means the input right now. And Ji minus 1 means the input before. Ji minus 2 means the input before that. I minus 3. It's some kind of symbol that we are using. So it is the function of every history of the input. So this is the concept of the memory. So the system has some kind of memory from the previous inputs that came to the circuit. Or better, we can write W is a function of inputs, the current inputs. So the current inputs, Ji, and the current state. And this current state has been created from all of the inputs before. So this Si is somehow dependent on Ji, Ji minus 1, Ji minus 2, and so on. Okay, so this is the sequential. And the key thing here is this feedback. So when you have feedback, again coming back to your circuit, it means that we don't have only inputs. We have something else also changing, also affecting. And the current, okay. So this is the current state. Now, in some time, we are going to change again, to change inputs. So when we are going to the next time slot, before going to the next time slot, depending on the current state and the current input, we are building the next state of the circuit. So the next state of the circuit is dependent on the input and the current state. So it becomes the next state. As soon as you move to the next time slot, then this next state becomes the current state. So it is SI, and then the W will be a function of this SI and JI. So everything is building the next state. So the next time slot, this next state is the current state. Now let's start with example, which will be an SR latch. So the name says latch. Latch is something that locks something, getting something, and doesn't leave it. So it keeps it. So you see that this is a kind of memory element, a kind of storing something. We will see that. And SR means set reset. We will see it, how it works. So the name SR latch. Let's see what is it. Look at this circuit. If you look at it carefully, it is different from what we have seen before. What we had before was just some kind of gates, inputs going to outputs. But here you see, what do you see? You see a feedback. You see a feedback coming from here, going back to this gate. So it's different. So let's see what happens with this circuit. I could show it like that. They are the same. You see that I put this NOR gate down. I brought it down, and then this Q goes to the input of this gate, and this Y goes to the input of that gate. So I can write it like that, which is a better representation, and we call it cross-coupled NOR gate structure for SR latch, which we will discuss. The first one, we call it feedback model. And here, as you could see, I renamed Y to Q bar, because you could see that every time this output is the complement of the other output. So we call it Q bar, Q and Q bar. There are two outputs of the circuit. There are two inputs, S and R, and also there is some kind of a state that we are going to see. It will keep something inside that. Okay. So let's say Q is 0 now. Q is 0. And then we have S as 0, S as 0, R as 0, and Q prime is 1, and Q is 0. So this is the case. So if this is the case, you could see that this is 0. I could also calculate this one. Q is 0. So if Q is 0, then this is 0. Also S is 0. So 0 nor 0 is 1. 0 nor 0 is 1. So this is 1. Okay? So if it is Q is 0, then based on this circuit, we have 1 at Q prime. Okay? So this is the timing diagram of the circuit. So this is the first time slot. Now, for the next time, we are going to make S as a 1. So I write it in another color. Okay. So now we are making S 1. So S becomes 1. So when S becomes 1, this one comes here. 1, now 1 or nor 0 is 0. Now it becomes 0. And this 0 comes here. Here we have also 0. So again 0 nor 0 becomes 1. Okay? Now you could see that Q is 1 and Q bar is 0. Okay? So this is the timing. So S became 1, R is still 0, so Q prime becomes 0 and Q becomes 1. Now let's say that again S becomes 0 like before. So now with another color. So now S becomes 0. So S becomes 0. What was here? I should have written by blue. So blue. We had 1 here. So this is 1 now. And we have 0 here. So we have 0 here. Okay. Now we have 0 on S. When we have 0 here, and then we have 1 up, so when we have 0 here, then we have 1 up. So 0 and 1 is 0, or nor 1 is 0. So we have 0. And then we have 0 here, and again here is 0. 0 nor 0 is 1. Okay? Yeah? Agree? No, we are noring. We have a cross-coupled nor here, so they are affecting each other. So now we have this. S becomes 0, R is 0, then Q prime remains 0, Q remains 1. What do you see here? Yes?
For the second example, what is the second input when you first put S and R through the NOR gates?
I didn't change it. So at the beginning, S was 0, R was 0. Then I made S as 1 and R remains 0.
But like, because it goes through, right? But there's 2 inputs, but the second input hasn't been initialized yet.
No, it is something there. No, it is something there. Let me see. What do you mean? So you see. So you are talking about going from red to blue or from blue to green? Red.
When you start at 0, let's just say S goes to the second NOR gate, right? And there's another input.
No, could you tell me which position? Because we were here at the beginning, here, red. Then we went to blue, and then we went to green. So which part are you talking about right now? Red, blue, blue. Okay, okay. So if you are talking about blue, it relates to that? Okay. For the first time, I told you, let's think that Q is 0. Okay? For the first time, I told you, let's think Q is 0. Then, based on that, I found Q bar is 1. And then we are moving. So it's there. So we don't need to do anything. So from red going to green, this is the thing, but we only change S to 1. Okay? We only change S to 1, so S becomes 1 in blue. Okay?
One thing I noticed with this is that once we switch S to 1, the state changes, but when we change it back, the state doesn't change.
By a state, you mean output?
Yeah.
No. So it's not a state, it's output. Yeah, the output doesn't change. Yeah, that's good. So let's finish with that. Yeah. Are you finished? Did you get it? So in the red to blue, S becomes 1. Okay? Look at the blue one. S becomes 1. And R still is 1. Oh, so blue, not the green. So R is 1. 0. R is still 0. S becomes 0. So 0 comes here, and at this time, what was the blue? What was the input is 0, and we had 0 coming from here. So 0 will change to, I have to write it again. I did it at that time. You see, S is 0. R is 0. So S is 0. No. So S is 1. Sorry. S is 1. R is 0. 1 coming here. 1 coming here. But so when 1 coming here, 1 nor 0, because we had 0 before, 0, Q, 1. So we have Q, so we have 1 nor something, so it will become 0. Okay? So Q bar becomes 0. When Q bar becomes 0, the Q bar coming here, and we have 0 from R coming here, 0 nor 0 gets 1. So for the next slot, the second slot, we get 1 for Q, 0 for Q naught. Then we changed again S to 0. Look at that. When we changed again S to 0, so 0 comes here, and from the top we do have 1, so the output will become 0, or still remains 0. It was 0, so it still remains 0 here. But this 0 comes here, and here 0 again, 0 and 0, so the output remains 1. So the output remains whatever it was, as David said that it kept the state, but the outputs didn't change. Okay. Look at here. At the first column, you see S is 0, R is 0, and Q is what? Q is what? Q is 0. But at the third column, S is 0, R is 0, but Q is 1. Q is 1. Q is 1. You see? The Q, the output of the circuit, doesn't depend only on the inputs. If it was only inputs, when our inputs are the same, 0, 0. So the output should be the same. But here you see the inputs are 0, 0 at both time, here and here, but the output is not the same. Did you see? The output is not the same. So it means that there is something inside the circuit that affects the output in addition to the inputs. Now let's move to the next slot. What is the color? Okay, the color is orange. So I will use orange. So now what do we have now? Let's write it. We have with green. At the green state, we have 0 on S, we have 0 on R, we have 1 at Q, and we have 0 at Q prime. Okay? Now we go to the next state, and we change R to 1 now. So R is getting 1. Orange. So R is getting 1. S is still 0. So this becomes 1. When this becomes 1, 1 coming here, and then from the Q prime, we have 0 here. So 0 nor 1 becomes 0 now. And then from here we have 0, and then from here also we have 0. Here is 0, 0, 0. So 0 nor 0 is 1. Okay? Now Q and Q prime change. Both of them are changing. Q becomes 0, Q prime becomes 1. Okay? So that's the next step. That's the next slot, time slot. Now we change again. We move back R to 0. So right now it is the case that we have it right now. We have 1 here, 1 here, we have 0 here. Okay. So now we change it. What's the color? So it is red. Again red. Okay. I use red again. Okay. R becomes 0. R becomes 0. S is still 0. We don't change S. R becomes 0, so here we have 0, and then we have 1 at Q prime, so we have 1 here. 0 nor 1 becomes 0. 0 nor 1 becomes 0, yes? Huh? Get 1? This one coming from here. This one, yeah, here. This is connected to that. Okay? So this is 1. So we have 1. And 1 nor 0 becomes 0. Now we have 0 here, so this becomes 0. And also this is still 0. So 0 nor 0 becomes 1. Okay? So Q is 0, Q bar is 1. Good? Now let me talk a little about this. Please look at this carefully. Look at this carefully. When I will give you some statements and then we verify it with the circuit. When S is 1 and R is 0, then it means set. So it will change the Q to 1 and Q prime to 0, regardless of the state. When S becomes 1, R becomes 0, then it will change the Q to 1, sets it, set. S is 1. When R becomes 1 and S is 0, then it means reset. So Q gets 0, Q bar gets 1. When S is 0, R is 0, then it means that no set, no reset. Just keep it, whatever it, this is the kind of memory that we have. Whatever it is, keep it. So if the previous state, Q was 1, it remains 1. If the previous state, Q is 0, it remains 0. Look at here. S is 0, R is 0. Q remains. Q bar remains. Here, again, S is 0, R is 0. Q remains, Q bar remains. You know, it is a kind of memory that we have built. When we want to change it, we use S and R. S and S1, R0, make it 1. When we want to reset it, make it 0, we put R1, S0. But in other time, S and R are both 0. You could ask a question here. Nobody asking? If you don't ask, I don't answer. I don't go to it. So let's move. It has memory. You see, it has memory. It is not only dependent on the inputs. We have same inputs, but different outputs. And it was because of the memory that it had. Output depends on the state coming from the circuit. When we are in this state, output is the same as before. When we are in this state, so output remains as it. When S and R becomes 0, yes. So S R, you say S R are 1 0 now, and then we go to 0 1. So it's good. So when we are here, it means that Q gets 1, Q bar 0, because we set. Okay, we set. S is 1, R is 0. But here we are resetting. R is 1, S is 0. So for sure, Q prime becomes 1, Q becomes 0. And this is something that you could see here in our timing diagram. Let me show you. Where was that? Let me erase everything. Here, you see S. S is 1, R is 0. So this make Q as 1. Here, we have R as 1, S as 0. This will make Q bar as 1 and Q as 0. Okay? And in this situation, it doesn't depend really on the state. So we have a set and resets which will do its work. It stores a new value in the element, which is either 0 or either 1. But if we don't want to change value, then we leave S and R as 0, as R as 0, and it doesn't change anything. So it has a memory. Yes?
If we were to set it and then enter 0 and it does nothing.
Yes.
What if we were to then, after the 0, set it again? Does it also do nothing?
If it is set, yes. It's actually it doesn't. Like here, I have the same thing here. No, I don't have it as an example, but I could build. Yeah, if it is S is 0, S is 1, R is 0, so the Q becomes 1. Then you say that S is 0, R is 0, so it means that it keeps it. So again, Q is 1. Then you change S again to 1 and R is 0, it means that set it, so it's again 1. Yeah. Yes?
What if you have S set to 1 and then you set R to 1?
Okay, that's the question that I was afraid that you asked. Yeah, that's the question that I didn't go through it. So 1 1, we call it an unwanted situation, unwanted input. Why? Because if you put 1 1 here, maybe I have it in the next slide, then you somehow destroy the memory. So the memory is not doing what it should do. I will give you the example. So in this architecture, in this implementation, which is SR latch, you have to make sure that S and R don't become 1 together. One of them should be 1, the other 0, so it works. It either sets or resets. And if both of them are 0, it means that memory keeps its value. The Q remains as it was before. 1 and 1 changes. Maybe I have it in the next slide. So it has 2 states. As you could see, it has 2 states. Either Q is 0 or Q is 1, and either Q prime is 0 or Q prime is 1. So it has 2 states. And that state somehow is going back to the circuit and it affects it. So with this kind of feedback, we made a memory here. Okay? Set reset latch. We call it SR latch. It is a latch because it keeps the value, locks it. What is here? I don't know. Y is feedback. Yeah, this is the feedback that we made it. So, and this feedback made it as a memory. Okay. So, if we want to write the truth table, something like truth table, or we call it here excitation table. We have something like that. So this is the transition table. Look at here, carefully. When S and R are 0 and Q is 0, the next state is also 0. Keeps it. It keeps it. When S is 0, R becomes 1, the Q will become 0, regardless of the previous state. So this is 0. When S becomes 1 and R is 0, then Q becomes 1, whatever it is. When both of them are 1, it is unwanted, so don't look at it right now. When we have 0, 0 and Q is 1, so 0, 0 means keep it, so the next state is 1. When it is 1 and then we have 0, 1, 0, 1 means reset it, so it is 0. When we have 1 at Q and then we have 1, 0, then it means that set it, so it becomes 1. It is 1, but it's still 1. It becomes 1. When 1 and 1, so it is not correct. It is unwanted. So this is the transition table. We could write it a better way, which we call it excitation table. So with excitation table, depending on the inputs and the states, which our state here is Q, we make the next state. So Q plus the next state, if they are both 0 and 0, the next state is as the previous one, whatever it is. It is either 1 or 0, whatever it is. But if you have 0, 1, the next state would be 0 for sure. It resets. If it is 1, 0, the next state would be 1 for sure. If it is 1, 1, it is not valid and it is not good. We call it excitation table. That's good. That's to give you the idea of how it does. 0, 0 keeps it, 1, 0 sets it, 0, 1 resets it. But this is not a good, illegal, no memory. The memory is going to be destroyed, and somehow we lost. It's lost. So yes, it saved something. Do you agree? It's saved. When you change S and R to 0, it saves whatever it has. So it is a memory. Yes?
So Q plus, that means
the next state.
So what Q is like keeping? So if it's 0, then Q keeps the same state, but if it's 1.
So the next state would be this Q plus is Q.
Oh.
Okay?
Because it was just one symbol, 0 or 1.
No, this was you have three things here. You have S and R and Q. Based on that, you build Q plus. Maybe I could write an equation. Q plus becomes, when both of them are 0, it is Q. So it is S bar R bar Q plus. When it becomes 1, when R is 1. So how do I write it? When R is 1 and S is 0, it becomes 1. So R is not. When R is 1, when R is when S R not. S R not. The mean term is S R not. S R not. So this is the equation. S bar R bar Q plus R bar S. So whenever R gets 0 and S gets 1, then if R gets 0, it is 0, yes, 0, 0, yes, And when S is 1, R is 0, it becomes 1. Yes, 0, 1. Yes, that's good. That's good. That works. Yeah? Q plus is S bar R bar Q plus R bar S. Could you try it? You see it works. And Q plus is the next state of the circuit. Any questions? Okay. Now, we are going to introduce a new concept which you have heard before, which is clock. Clock gives us some kind of timing. Timing is good in memory because for us, when, for example, as an analogy to our brain, we want to memorize something. Okay, now I am going to memorize this. SR latch means set, reset, latch. So at the time, I gave input to my brain and asked the brain to memorize it, to store it. Okay, there is a timing in our brain, so we use it. Whenever we want to store something, we pay attention to it. So it has a timing. And also, it will give us some other advantages, which I will show you later. So we need timing. It's good to have timing. And for that, we will introduce a concept of clock. So what would it be? With clock here, we mean if the clock is 1, then it works. When clock is 0, so the clock is something like that. It is like that. So it goes from 1 to 0, 0 to 1, 1 to 0, 0 to 1. So that's it. When the clock is 1, then we want the circuit to work. This is the timing that we were talking about. When the clock is 0, we don't want anything happens. Okay? So how do we do that? Whenever we want to mask something with something, what do? We had before like that. We have enable at decoder. What do?
When you set the input of a component to 1, if it's like a low input.
How to mask it? So if clock is 1, we want it works like it is. When the clock is 0, we don't want it to work.
Could we AND it with a component?
Perfect. Yes, exactly. And is very good for masking. So if we have some kind of this, so our S is going to be ANDed with clock, and R also will be ANDed with clock. And if we put S and R like this, then we have a clocked SR latch. What does it mean? It means if clock is 0, then clock is 0, regardless of the value of R and S. Here we have 0, here we have 0, so, and we talked about 0, 0, when S and R are 0, then it means that it doesn't do anything. It keeps its value. The Q will remain as it was before. But if clock is 1, then we can set or reset. Then if clock is 1, then we can put S as 1, R as 0, make the Q 1. Or we can set R as 1, S as 0, then we can reset it. Okay? So that's it. We have made a clocked version. We will see how it helps us for making something which will not going to the that situation, one situation that we don't want. We will see it later. But before that, having a clock is very good for synchronizing all of our elements in the circuit. Because we have a circuit, lots of combinational things in the circuit. One of them is this one. There are so many things in our circuit. And they are doing, and they have different delays and so on. So to make them synchronized, because they have different delays. This part of circuit has a delay of 10 nanoseconds. This part has a delay of 8 nanoseconds. This part has a delay of 5 nanoseconds. So to make all of them synchronized, we put a clock there, for example, with a cycle time of 15 nanoseconds. So we give them clock. So when they have clock, they start working, and then we remove the clock. So they are still working, but the state doesn't change. They are working inside. And then everything is ready, after 15 nanoseconds, for example, we bring the next clock. So at the next clock, everything was ready. This part had a delay of 10 nanoseconds. This part 8 nanoseconds. This part 12 nanoseconds. This part 5 nanoseconds. So they have all prepared their outputs. Now the outputs are ready. The next clock comes and it works. So with clock, we synchronize everything. It has a very important role. So in all of the circuits from now on, I guess you could see the clock because of the synchronous design. Yes? You have to calculate. So either you calculate it by hand, which is very difficult, or you do the simulation. You design your circuit, give it to Quartus. The Quartus will calculate the delays and say, this is, for example, the critical path, the longest delay. So you should have a clock more than this, the cycle of. And so the concept of critical paths becomes very important. If you have different passes, this is 10 nanoseconds, this is 8 nanoseconds, this is 12, the critical path determines your clock speed. So you have to pay attention to that critical path, and if possible, make it shorter to get a better clock. Because, as you know, clock is synchronizing everything, and we select the clock as the longest path. Okay. So this would be the excitation table for this circuit. Now here, if we have 1 as a clock, then it works as before. 0, 0 keeps the previous state, 0, 1 resets it, 1, 0 sets it, 1, 1 is not valid, and if the clock is 0, then the state remains. Because if the clock is 0, we have 0 here, we have 0 here, and it means that Q is not changing. So it's very good. We have a clocked SR latch. And it is very good for synchronization. And also, we had talked about, you were going to talk about that as hazard. You remember? We had hazards. Hazards was some kind of effect that happened through the delays. And we have a glitch, and then it became normal. We had a glitch. So if we have clock and we look at the circuit at specific times, so we gave our circuit a time to do whatever it wants. So even if there is a hazard, the circuit gets a glitch and then come back to the expected value that we want. So the clock could also solve our problems of hazard. At the clock points, we look at the circuit, and that time we actually pass the hazard. You remember, hazard was, for example, for 4 nanoseconds, but after that, the circuit was okay. The output was okay. Now we are going to build another structure using this. We call it D-latch. D-latch. What do you think this D means? D. Yeah, it's hard to guess, but it is data. We will talk about data later. Okay. D-latch. Okay. So this was our last circuit. If you look at S and R here, then when this is S and R small. These are our main S and R, and these small S and R's are clocked and coming there. So when we have when we have S0, R0, clock 1, so it's ascending. But here, this is the point that I want to say. Here, we have R1, S0, and clock 1. So if R is 1, S is 0, then our little R and S, our small R and S are also 1 and 0, and then the circuit works as before, so it resets it. Yeah, it resets it. When we have 1, 0 as capital S and capital R, the main inputs, and clock is 1, so the little S and R, they get 1 and 0, and they work as a day. So it resets and resets. This situation, this combination, we don't like it. It is unwanted. And this combination, S and 0, S and R, capital S and R becomes 0, and clock is 1, we have 0 and 0, 0. But let's say if the clock is 0, regardless of capital S and R, the little s and little r are 0. Okay? So, if the clock is 0, we have somehow s and r 0, the thing that keeps the states. So, a small s and r have 0, 0 also when the clock is 0. So, we have 0, 0 here. We have 1, 0 here. We have 0, 1 here. And we have 0, 0 here, which we can get rid of it and don't look at that. How? This way. So we don't need that because we get it by clock. This is also, we don't need it because it is unwanted. It destroys our memory. So we make it like this. Look at here. Now here, capital S, and capital R. So they become complement at each other. We have one input here, one input, and that input is complemented and going to the next input. You see? So with this situation, S and R are always S and R capital. S and R are always complement of each other, 0, 1 or 1, 0. And that's good because we wanted to have 0, 1, 1, 0, and 0, 0, not 1, 1. 1, 1 was not good for us. So with this situation, actually we removed 0, 0 from here. We cannot have 0, 0 here, but we can have 0, 0 here when clock is 0. Okay, you got it? So with a clock and one input which inverts for the other input, S and R, we have built our preferred states, our preferred inputs. 0, 0, 0, 0, we build it when clock is 0. 0, 1, when D becomes 1. It becomes, 1, 0 is when D becomes 1. S becomes 1, R becomes 0. 0, 1, when D becomes 0, we have 0, 1 for S and R. Okay? Simple? Don't follow? Maybe I told it fast. Let's look at this circuit. Look at here. I don't go through the concept of making it. This circuit, look at this circuit. So we have, okay. So we have D as the input. Let's say D is 0 now. When D is 0, then this is 0, and this is the invert of that, so this is 1. And let's say clock is also 1. So here 0 and 1 we have 0 here, 1 and 1 we have 1 here, and here it is our famous R and S. So S is 0 and R is 1, so the Q becomes 0. Because R is 1, we are resetting. R is 1, S is 0. So this is when D is now with the next color. So let me write 0 here. When D is 1 now, when D is 1 now, when D is 1, then D naught is 0 and clock is 1. So 0 and 1 becomes 0. Here we have 1, 1 and 1 becomes 1. So we have our famous SNR, our small SNR as 1, 0. So it means set. So the Q becomes 1. Okay? That's so two things that I wanted to set or reset, I did. But what about 0, 0, which means that keep the state. The clock is 0. When the clock is 0, let's with another color. No. Orange. When the clock is 0, then here we have 0, here we have 0. So it is 0, 0 for our cross-coupled circuit, and the Q plus would be Q. Still remains there. So this is the new excitation table. And it is very good. Look at it, how good it is. Why? Because we are introducing a concept of data. When data, we put 0 as the data, and we give a clock, the Q becomes data. You see, when D is 0 and we give a clock, it becomes 0. When D is 1 and we give a clock, it becomes 1. So we have introduced a memory element which stores a bit, either 0 or 1, based on a clock. We give clock, it stores in the output, and it remains there until the next clock. The next clock, again, if D is changing in the next clock, the Q is changing. If not, it's still there. Oh, it's a very good memory element. And the other beauty about this is that it doesn't have that invalid state of 1, 1 that we were worried about. Yes?
Could we just say that the latch is basically a set reset latch, it's a clock, where S and R are basically just
the complement of each other. Exactly. That's the structure that we built. So we started we SR latch. Then we clocked it. Then we made it D latch. So the D latch is coming from SR latch, but with this modification that we have done. So this is the another structure. So this is very good. The excitation table is very good. Q plus is D. So where is clock? Where is clock here? Clock is a very valuable thing. You shouldn't play with it much. Clock is clock. So clock means going to the next state. So the clock is showing itself here with this plus. So clock, you don't write it clock here. Clock, you should respect it. You shouldn't bring it here. Clock is very valuable. But you write about the other things. Q plus is D. Very simple characteristic equation. The characteristic equation of D latch is Q plus is D. Okay? Questions? And the symbol is that. So this is the data input, and this is the output with a clock. Yes?
So for the first example, are we timing the clock with when S and R are 1 and 1 so that it doesn't?
It doesn't happen anymore because they are inverted. So
I mean the first example, like if we were to use the first example.
oh Yeah, that's not good. If you put S and R and 1 and also have a clock, it's bad.
Would the clock be timed with when it becomes 1 and 1, so then it doesn't happen?
But you are saying that the clock is 1, no? Clock is 1, S is 1, R is 1. It is a very bad situation.
I'm saying you time the clock so that clock is 0 when S and R are 1 and 1, so that it negates that happening.
When I was saying that, I told you when clock is 0, then you have 0, 0 here. So really you don't need to have 0, 0 here. So we only need 0, 1, 1, 0. So it will give me the idea of putting this inverter here. That's what I told you there. But it is up to you. If you design your circuit very carefully, so and you know that when S and R are 1, the clock should be 0, yes, that's good design. But it is you that you design it. So you as a designer could design something that the clock isn't become 1 when S and R are 1, both of them. It's up to you. I didn't do anything. It's just a circuit. So if you have this circuit, you can put 1 here, you can put 1 here, you can put 1 here. And this is not good. But you shouldn't do that.
I'm confused at how, besides timing delays, what the point of the clock would be.
Oh, the clock. There are first was the hazard, as you mentioned. Second is the timing. So I told you it synchronized everything. You make a clock, it starts doing, and then you remove it. So the next clock comes, then everything has been prepared during this time, and now everything is ready, we use it again. So it synchronizes everything. It's very important.
So it disables the network until
the next state coming inside. So the current states are working. They are working, and they have I told you, for example, this circuit takes 10 nanoseconds. This takes 8 nanoseconds. So they are all working, but there is no clock. So nothing changes, but they are working. Then the clock comes. So the next state is ready now. When the clock comes, it goes to effect. And this is synchronization idea. Now we are going to our next structure, master-slave flip-flop. Okay, let's start by a project. We would like to build a tally counter. This tally counter, you know it. When you press the button, it counts one more, and there is something that you could reset it. You could bring a value to it, the initial value, which I don't look at this right now, but look at this. So whenever you press it, it goes one more. 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 2, 3, 4, 5, and go on. Okay? We would like to build something like that. So we have a button, and then after we click the button, it is incremented. It's like a counter. Okay? So what do we use? What do you suggest? Yeah?
Well, I'm thinking for the button that increases the tally, we're going to need something that once you click it, it changes its state to 1, but then once you let off, its state goes back to 0.
So what concept do we have for that? When it is there, it works, it increments, and when it is not, it doesn't. A clock. So the clock works there. Very good. And what about the digits? So we need some kind of a store for digits, and when the clock comes, it increments. So what do we use for digits? The latch. We know the latch now. So let's use it. So we have this D latch, and each D latch stores 1 bit. So the digit that we have is a decimal digit. It has how many bits? 4 bits. 4 bits is enough for every digit. 4 bits, because 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, up to 10, which up to 9. 1, 0, 0, 1. That's it. So that's the counter that we build. Okay? So we need 4 bits. So we use 4 bits. Now we have 4 D latch. And these stores the number. The 4 bits stores this number. But we would like it to be able to increment it. So whenever the clock comes, for example, it goes to the next number. How do we do that? Yes?
If the translator bit is 1 and you click the button, you have AND going to be D of the next one?
Okay, but how? Because, for example, this is, let's say we are now at number 5. Number 5 is 0, 1, 0, 1. So it is 0, 1, 0, 1. Now we are at this state, 5. So what happens when we have clock?
So you take the Q and put it into the input.
What do I put as the D input? Yeah, it's very good. What?
Q?
Huh?
Q.
Okay, so if you put Q, so it still remains 1. It's 1, it's 1, it's 1. So this is 1 now, and it's again 1. It's again 1. It is 0, so it's again 0. So D flip-flop, D latch gets the data input, puts it the output. When you put Q as the input, so it's a loop. It's always the same. Q. So if it is 0, it's still 0. If it is 0, it's 1, it's still 1.
So would it be Q naught then?
But that's not good. But it doesn't count. Because, for example, let's see what happens if we put Q naught. So if we put here, and here, so let's start, for example, with 0, with 5. With 5, I told you. 5 was 0, 1, 0, 1. And then the next number would be the not of that. Let me write it with blue. So the next number would be 0, 1, 0, 1, which is how much? 8 plus 2, 10. So we were 5, and then we went to 10. Then again, the next clock, this one becomes 0. So the next clock, this becomes 0, this becomes 1, this becomes 0, this becomes 1. Again, we back to 5. So we were at 5. Then we went to 10. Then again 5, 10, 5, 10 with this sequence. So what do we need to put there?
So the clock and Q?
Yeah, clock. Yeah, the clock is there, but what do we need to put for the D? So the next Q would be the next number. You see, I told you here we have 5. What should be the next number? After 5, 6. How do we get 6 out of 5? Plus 1. And then from 6 plus 1, 7, and so on. So if we put some kind of incrementer, plus 1 function, in our combinational components that I was explaining for you, we had an adder there, but we didn't touch it because of the time we came here. But we have an adder. So if we have an adder plus 1, then that's good. That's good. Why? Let's see. Here we had, for example, 5. 5 was what again? 5 is 0, 1, 0, 1. This 0505 goes here. You see, it comes here to the adder, to our incrementer. So the input value of the incrementer is 5. So what would be the result of the incrementer? 5 plus 1. What is that? 6. So if I want to write it in binary, 6 would be 0. So let's write it with blue. 0, 1, 1, 0. Okay? This is 6. So look at this. Now the value 6, as they are at the front door at the D, and they are waiting for the clock to come, and when the clock comes, they go to the output, and output becomes 6. Yeah? And when they go to the output, and output becomes 6, these 6 now comes here. They are connected. And the next value is 7 comes here, and it is at D location. Okay? Good? We build a counter. So every clock adds it. 1, 5, 6, 7, 8, 9, and so on. Good? Okay. Saying this problem would have a bonus point. Whoever says it first gets the bonus. Yes?
This is just one digit. The counter has 4.
No, you put 4 of them together. Okay. So that's good, but not the problem. So we build it. Yes?
Currently we're counting in binary, and I'm guessing for like a tallier, we want to display that in decimal.
Yeah, we should somehow limit it. Yeah, you are right. But this is not what I am looking for. I am looking for something that is very bad. Worse than that. Yes?
Is it the initialization?
Yeah, we have started something. Yeah, all of you're right, but it is not what I am looking, because you see that this is a problem of our design. Yes?
If you hold down the clock, it'll just keep counting up.
Why do you hold on the clock?
Like if you just hold on, it will just keep like ticking up.
So don't hold on.
So you need a way to switch.
That's correct. So remember, you have the bonus. Clock is this. So what's your name? Ben. What Ben is suggesting is that if this is the clock, so clock is 1 for a while and then going to 0. So when the clock is 1, so the value of 6 is here, the clock is 1, so 6 goes to the output. When 6 goes to the output, because the clock is 1, so 6 is here, and 6 is connected with wires to incrementer. And incrementer is a combinational logic. So the incrementer increments, and it becomes 7 here. If this delay, which is not much, it is just a combinational circuit, if this delay is less than this interval, then we have 7 here, and 7 goes out. With one clock, we made it 6, 7, 8, 9, and it goes until the clock is on, and then come. So the first thing, the suggestion would be like what I told Ben. Don't hold it. Make a very small clock, a very narrow clock that is bigger than the delay of this. So you don't change it. But it is not practical. We don't know what is the delay. It might, the delay might get lower sometimes. So there are lots of causes that could change the delay of the circuit. So it is not a good idea. Anyhow, you told the right thing, and this has a problem. We call it that this D latch is transparent now. Whenever clock is 1, it moves, it passes, transparent, goes there, which is not good. We would like to make something happen. So we are out of time now. I just give you the idea, the analogy. Do you have any solution for that instead of, in addition to this narrowing thing?
We need to find some way to turn like the clock off once it's incremented once.
But you can't. Always, when you are thinking about the delays and playing with the timing, it might get it might not work because it changes. The delays are not good. Yeah?
You make 1 clock for all 4?
It is 1 clock. It's already 1 clock. Yeah. You see, this is 1 clock, and the same thing goes here, the same thing goes here, the same thing goes here. 1 clock. But all of them together coming inside. 6, 7, 8, they're coming inside. Let's say that we have a room, a hot room, in the winter, when you want somebody goes to a building when there is a cold weather outside, and in the building we have a good weather. What are we worried about? If you open the door, so the wind coming inside and the cold coming inside, that is not good. And then we close the door very fast. This is one solution, which is not good because somebody might be slow, so it takes time to move inside the building and then shutting the door. What do we do? Perfect. That's the solution that we do in our buildings. We put 2 doors, interlock door, so it comes inside a room. Then that door is being closed. Then the next door is open, and that room is better. The weather is not too cold. This is exactly what we do here. So we will see it in the next lecture. How do we do this kind of door? We have a door. We make them come inside, but not going to the output stage. Come inside, but leave it there. Then the next thing. Okay. Have a good weekend, and hopefully see you on Tuesday.